Hi, here we are on Chapter 18, Reaction Rates and Equilibrium, Section 2. So let's continue. How can we compare like a bicycle race to chemical reaction? Well, if we look at the famous Tour de France bicycle race, it crosses some steep mountains with heights of 1,900 meters or more. That requires a lot of human power and energy to get up and down those mountains. Well, that has something to do with the rate that they go at too. They're going to go a lot faster going down that mountain than trying to get up it. So let's check out how that applies to chemistry. One of the things that we have when we talk about rate is something called K. Okay, so if we look at K, we're going to see a little k here. All right, and it's right here. It is a constant that we're going to talk about in helping us understand how quick a reaction occurs. So let's continue and see something called a rate law. Okay, one of the things we have to think about is what are the concentrations of our reactants? The more concentrated it is, probably a better chance that the reaction will occur more quickly because the particles can see each other, or not necessarily see them, but they're more apt to collide. So let's just look at something that decomposes to something else or changes to something else. So here we have a reactant called A, and it's going to make a product called B. So the rate at which A forms B can be written as a change in A with time. So this is how we write it. So we have a change in A as time changes. So A should decrease as B is formed. So the rate at which that occurs is how much A has changed over the amount of time that has passed. Now, one of the things that's very important is that this relationship that we just talked about is proportional to concentration of A, or concentration of the reactant. So we can then write that since rate equals this, and if it's proportional to A, if we have some constant K, that's a proportionality constant, okay? So in other words, we change our proportionality to an equality by using this constant. Okay, that's all it is. So if we rewrote it, we could write rate equals K. Now I'm going to write it in script, because if you're writing by hand, you should write this K in script, and concentration of A. So that's basically how we would do it. A lot of times we're going to cancel this part out and just write it simply like this. As I said, this is called the rate law. And it relates for us the disappearance of our reactants in a certain amount of time, and that is proportional to the concentration, and we can make it an equality by using K. And we're going to talk about how we can find out what K is in a second. Okay, the specific rate constant is a proportionality constant. Okay, so we're able to use this K to make this rate an equality. One of the things you should know is if K is large, if K is large, so if K is large, then the rate is quick. Products forms quickly. If it's small, the products form slowly. Okay, so this determines basically how fast. Okay, so we can look at that K and it will tell us something about how quickly the reaction occurs. Now we're going to call our reactions first order, second order, third order, etc. A first order reaction is basically thought of as a power to which the concentration reactant must be raised to match the experimental data on a concentration and rate. So we're going to be able to tell the order by the exponent, is another way of saying this. Okay, in a first order reaction, the rate is directly proportional to the concentration of only one reactant. So a lot of times that's like an A going to a B. All right, A will disappear at a certain rate going to B. You could also have two things combining, but the rate might only be with one of them. It could still be first order. Okay, so as I said, any kind of reaction, as the reaction occurs, you're going to keep on decreasing the amount of reactants or reactant that you have. And so we can see in this graph what happens. We see that the concentration of A is decreasing with time. It doesn't look linear, but we also see if we find tangents to this line, we'll see an initial rate, and then the slope of the tangent changes. It's very quick here, and then it's slowing down a little bit as time goes on. Why? Because there's less chance for collisions with the particles. So the reaction is first order. If A is reduced by 1/2, the reaction rate is reduced by 1/2. So it's proportional. So if you change your concentration, it's a direct relationship. So if you are 1/2 as much as what you started with, this slope is going to be 1/2 of the original slope. Okay? So this summarizes what I just said. Now there are higher order reactions. When you have two substances reacting, we can see from this equation we have our substances in capital letters and the coefficients for the balanced equation in lowercase letters. So those coefficients don't necessarily imply, however, what our rates are. So our rate equation is shown here. Oops, didn't want to do that. Is shown right here. And you'll notice since we have A and B, we have concentration of A and B. Notice we don't worry about our products. It's only the reactants. Now we have these two exponents, X and Y. That's what's going to tell us what order we have in terms of A and in terms of B. So if both A and B are first order, then the exponents will be 1 to 1. However, the overall reaction will be second order. Because 1 plus 1 equals 2. All right, so if X is 1 and Y is 1, the overall reaction is second order because we add the exponents. Okay, that's just what I said. Now, that's simple if you see it that way, but the actual order has to be determined experimentally. Now, let's look at this sample problem. We have, and basically we're looking at a situation where we have A going to B. All right, so we have A making B. And we don't know what X is yet. But we definitely know what the concentration is to start with, and then at a certain point in time. So we're basically, from here to here, we're doubling the concentration. All right? And so what we can do to find our order, if we have this information, which someone would have had measured experimentally, we can use this information to find our orders. Okay, so let's look at what was known in that situation. Okay, we know our initial concentration. We know our second concentration. We know the rate of the first when it's there, and we know the rate here. We don't know what the order of reaction is, and we don't know what the overall order is. Okay? So let's look at what the rate would be when we're at the first reaction. So here's our rate in the first reaction, the second data table. So if we take these two pieces of information and basically divide each of them by each other, we'll notice the K's drop out. So what we have is, since these is the same reaction, that's going to be the same order, so by our rules of math, we can turn this into parentheses, have A2 over A1, make that X, and have our two rates here. Since we have this data, we can solve for X. Watch what happens. So if we look on this page, we see that for rate 2, we had 12 times 10 minus 4 moles liters second. That was when the concentration was 0.1, and this is when it's 0.5. So we basically can cross this out, okay, and cross that out. So it's just pure numbers. So when we divide 10, the 4s can get crossed out. So 3 goes into 12 4 times. 0.5 goes into 0.1 twice, the x power. So 2 to what power is 4? X is 2. So that means if we wrote the rate here, rate equals K times concentration of A to the second power. Since that's the only thing it is, it's second order in terms of A and also for the overall reaction, because we add the exponents and that's the only exponent we have. Okay, you always check and make sure it makes sense. Okay, if the reaction was first order, doubling the concentration should double the rate. But the rate doubled 4 times rate 1. It went from 3, oops, it went from 3 times 10 to the 4 to 12 times 10 to the minus 4. So it quadrupled, okay? So it quadrupled, or was 4 times greater. So when you have a rate that quadruples, when you double the concentration, that is a second order reaction. What happens when the concentration goes from 0.1 to 0.2? Well, it basically goes from 0.1 to 0.2. We get 9.6. Let's go back. So if we look back here, we go from 0.1 to 0.2, and we go to 48. Again, that's 4 times greater. So it follows. It keeps on doing the same thing. So here we go. Here's a question. Okay, we're saying it's second order, all right? in terms of A. So I want you to figure out what the concentration would be when the rate is 1.2 times 10 to the minus 7 moles. Okay? So you know some things about it. Okay, let's write the rate law out first. What is the rate law? So we know that rate, let's do it up here. Rate equals K times A, because that's the only reactant we have, and it says it's second order. Okay? So what do we know? We know this. We know that rate 1 is 9. Let's do that here. 9.6 times 10 to the minus 7. And these things will all cancel out. And if we divide that by 1.2 times 10 to the minus 7, and this equals 2.0 moles squared over x squared. Okay? So that gives us our starting point. So I'm going to erase that by doing this. Well, we can go over here. Okay, so here it is written out. Oh, well, that's fine. It works that way too. If you solve for A2, you'll find out that it's 0.71 moles per liter. Okay? So what they did is they just reversed what I had, but you would get the same answer. Okay? So you could cross multiply. If you cross multiply 2 times 1.2 and 9.6 times A2 squared, then you are going to then divide by the 9.6 and you'll get